Hello Year 12. What we're looking at today is 3B from the textbook, Stationary Points and Turning Points. So again, our aim in this topic is to look at curve sketching, but using calculus. Okay, so we're always relating our stuff here to our derivatives, our stationary points, and looking at what's happening in our stationary points and around them. Okay, let's have a look. So there are three types of stationary points: a minimum, a maximum, and a horizontal inflection point. So language-wise, I've just called them stationary points, but they're also turning points. Okay, so we interchange between those names, and I would interchange between those names as well. Before we have a look at what happens in them, let's have a look below here. Here's our maximum. Okay, so a maximum one looks like a sad face, minimum, happy face, and a point of inflection happens like our cubic curve when our curve changes direction, but our derivative is going to be the same. So let's have a look at that mathematically. Let's have a look at the minimum turning point. So the minimum turning point is this one here. Okay, so a minimum moves towards the turning point and it has a negative dy dx to start with, a 0 dy dx, and then a positive dy dx. So let's have a look. That's what it says up here. The curve is decreasing on the left and increasing on the right of the minimum turning point. So here's our turning point here. That happens when our first derivative equals 0. Remember, when our gradient of the tangent is 0, that's what that's telling us. That's when our turning point happens. To the left of that point, our first derivative is less than 0. So our curve will slope in this direction. When we're to the right of the turning point, our curve will slope in this direction and our first derivative is greater than 0. And those parts are the things we looked at in our first section of the chapter in 3A. And that's what's happening down here with our minimum. Similarly, but the opposite is happening in the maximum turning point. We're starting off to the left of our turning point with a dy dx that is greater than 0. Then we've got it equal to 0 and then less than 0. And that's what this is saying here. For a maximum turning point, the curve is increasing on the left and decreasing on the right to the maximum turning point. So we might just get another highlighter color. So our turning point happens when our derivative is equal to 0. Okay, so our minimum looks like that. The maximum looks like this. So to the left of our turning point, our curve is sloping in the positive direction, our tangents would be, so our derivative is greater than 0. On the right of that turning point, our curve is sloping in the negative direction, so our derivative is less than 0. I think those are fairly straightforward. If you forget those, you just need to draw yourself and understand what the shape of the minimum and maximum looks like, and then think about what's happening either side of that derivative. You may have just heard a cat meowing in the background here. A point of inflection. So these guys are the points of inflection. These are curves, and we're used to seeing them in a cubic curve, just y equals x cubed, where it comes down, hits 0, 0, and then changes direction. That's what a point of inflection is. The curve is either increasing on both sides of the inflection or decreasing on both sides of the inflection. So over here you can see in this cubic, it's a positive cubic. It starts, and that's probably a good way to think of it. Your positive cubics have that direction. So we're in a positive direction, we hit our stationary point, and then our derivative is positive again. With a negative, we're going in the negative slope direction. So dy dx is less than 0. When we hit our stationary point, it's 0. And then when we move, where dy dx is less than 0 again. So if we found our stationary points of our functions, if we found dy dx and let them equal to 0 and found our stationary points, we could then analyze what happens each side of that stationary point, and that would tell us what kind of curve we have. So, and a lot of the time you're going to use some of the knowledge that you already have on those curves to help you with that a little bit. Let's look at example 1. Find the stationary point on the curve y equals 2x cubed and determine which type it is. When they mean which type, is it a maximum, is it a minimum, or is it an inflection point? Now, you should be able to look at this curve anyway and go, well, yeah, this is going to be an inflection because it's a cubic. but not always with all your cubics. Some of your cubics may be a little bit sideways, so you do get maximum minimums. So don't always assume that. Okay, so stationary points or turning points. Remember, they're the same thing. They have a maximum and a minimum. You might call them minimum turning points or maximum turning points. They're also stationary. They happen when our first derivative, dy dx, equals 0. Remembering, the reason they happen there is because at that turning point, the gradient of our tangent, which is these lines here up on the graphs, the gradient of those tangents is 0. And when we find dy dx is finding the gradient of the tangent. So that's why we're finding dy dx is equal to 0. So what is dy dx of this function? Dy dx is 6x squared. When does that equal 0? Well, 6x squared equals 0. We'll divide by 6 when x squared equals 0 and when x is equal to 0. So x equals 0 is the x point of our turning point, but we need to find the y. Y will be equal to 2 times 0 cubed, which is 0. So 0, 0 is a stationary point. So what I've just drawn up to the right here is a little box that can tell us and help us find the slope of our function either side of our turning point. So I popped x, a y dash. Notice not y, it's y dash or dy dx, same thing. We want to have a look at what is happening to our first derivative either side, and we want to have a look at the slope. So at 0, our dy dx is also 0, and our slope, there isn't a slope because that's our turning point here. This one is our turning point. We want to have a look at what's happening either side of that turning point. So let's just pick some easy numbers. Let's pick 1, and let's pick -1. And we're popping it into y dash, okay? And that is, we'll highlight that over here. What's that one here? Okay. So when x is 1, what does y dash equal? Y dash is equal to 6. And that is positive. So our slope is going that way. When x is -1, let's pop that into y dash. -1 squared is a positive. So we get 6 again, which is positive. So we can see that if here was our turning point, to the right, we're sloping in the negative direction, and to the left, we're sloping into the negative direction point. So it is an inflection point. To be a little bit clearer, I'm going to write 0, 0 is a stationary point. All right. That is an inflection point, and that's what I want my answer to be. Okay, so for the next one. Okay, find any stationary points on the curve. F of x is equal to x cubed minus 3x squared minus 9x plus 2. So you don't panic when you get a cubic, because when you find your dy dx, you're going to end up with a quadratic. So that's something that we can definitely work with. So stationary points. When do our stationary points happen? They happen when dy dx is equal to 0. Let's find dy dx. Let's differentiate our function. If we differentiate our function, we end up with 3x squared minus 6x minus 9. Now, we want to find where that is equal to 0. So we need to factorize this. So pause the video and have a go if you're doing it with me. I'm going to do it the way that I do it. You may do this slightly different. We will end up with the same solutions, but remembering that we're still adding to minus 6, but in case, instead of just multiplying to minus 9, we're multiplying to minus 27. That's what we're multiplying to. So let's have a think of what that could be. We're going to have 9s and 3s. Minus 9, I think, plus 3. Let's check if that works. Minus 9 plus 3 is minus 6, and minus 9 times 3 is minus 27. Now, here's an interesting thing. I could put that 3 of mine into either one of those brackets down the bottom. So I need to play around with this a little bit. I'm going to pop my 3 into here, and I actually could have done this a much simpler way. I'm going to pause this and have a look. So I'll keep going with this, and then I'll show you, oh my goodness, I forgot to do something. So I'm going to end up with this answer, which is going to give me values of x is equal to 3 and x is equal to -1. But I've done this a difficult way. I didn't even see it. I'm going to show you another way. So I've got my dy dx, but to factorise it, 3 is common to all those terms, which is so much easier. If I had to factorise out of 3, I would have got x squared minus 2x minus 3 is 0, which is a lot nicer to factorise out because it's a monic. So I'm looking for values that will add to -2 and multiply to -3 in that case, which is going to be -3 plus 1. So I end up with x is 3 and x is -1, same as I had over here, but just a simpler way to do it. So if you saw the shortcut by factorising out of 3, excellent. Otherwise, the other way wasn't too much harder. So that's our x values at the stationary points. Let's find our corresponding y values. So when x is 3, what's our y equal? When x is 3, y is going to be equal to 0, oh not 0, sorry, 3 cubed minus 3 lots of 3 squared minus 9 lots of 3 plus 2. When I pop 3 through, I end up with -25. So my first stationary point is 3 minus 25. Let's figure out what happens when x is equal to what? -1. When x is equal to -1, y is equal to... Sorry, I had a glitch with the video there. So when x is equal to -1, y is going to be equal to, not 3, but it's going to be equal to 7. And there's our second stationary point there. So what I've just gone and done ahead for us is to have a look at what the slope field basically is having a look at. So if we're putting x, y dash, and our slope here, we want to pop our stationary points here. So I've got -1 up here and 3 here. Y dash is 0 for each of those, and the slope is 0. Okay, so we're looking at values either side of that. So I've just picked 4, 0, and -2. Popping those into y dash, we can find out what the slope is either side of those points. So if I put -2 in, I'm going to end up with, what's that, 15, which is a positive slope. We know this is our stationary point, so it's got a 0 slope. Pop 0 in, it's between our two stationary points. We pop that in, we're going to get -9, and we're going to get a negative slope here because dy dx is negative. Next turning point or next stationary point here, look the other side of it, I'm going to get 15, which is a positive value. So what that's saying is the point -17 is a maximum turning point because we're going from negative to the point, positive to the point to a negative. Our second point, 3 minus 25, is going from a negative derivative to the stationary point and to a positive. So we're basically having the shape of the curve look like this. So I need to write that down because that's what the question's asked me. -17 is a maximum turning point because it goes in this direction like this. And 3 minus 25 is a minimum. I've just popped that into Desmos for us to have a look at. There we go. I'll zoom in there. There's our two stationary points. Our first one up here is -17 and our second one is 325. So as I move along that curve, I've got a maximum and I've got a minimum, which is what I think we had over here, a maximum and then a minimum. Let's look at the next question. Okay, the next question is a little bit trickier, this one. It says the graph of the cubic, f of x is equal to x cubed plus ax squared plus bx, has a stationary point at 2, 2. Find a and b. Okay, so we're not going to do this any different to the way we did our last one. Okay, let's just start and see how we go. So a stationary point. Remember, a stationary point happens when dy dx is equal to 0. That is when our gradient has no slope and therefore it is a turning point or a stationary point. So let's find dy dx is equal to 0. So, or f dash, whatever you would like to call it. So that is going to be equal to 3x squared plus 2ax plus b. A stationary point happens when that is equal to 0. We need to have a little think about what's happening. So our stationary point happens when this is equal to 0, and we would normally be solving that to get an x value. If we solve that to get an x value, there's our x value there, x equals 2. So this happens, we'll write that in there. This is when x is equal to 2. So I'm going to pop x is equal to 2 into this equation. So I messed it up a little bit. I'm going to move it down here to the left. So we're going to get 3 times 2 squared, which is 4, plus 2a times 2 plus b equals 0. So let's be careful with your algebra here. 4 3s are 12 plus 4a plus b equals 0. What else do we know? What would we normally do? When we would normally differentiate our function set to 0, we'd get an x value, and then we'd pop that back into our function to get our 2. So we know also, I'm going to write all that down, we know that f of 2 gives us 2, okay? So we're subbing in that 2 here into our function to get our 2. So that's going to give us another equation. So let's do that. So we know that 2 is going to be 2 cubed plus a times 2 squared plus b times 2, which I'm going to write as 2b. So let's fix that up. That's going to be 8 plus 4a plus 2b. I'll neaten it up a little bit. I'm going to just subtract 8 from both sides. So I'm going to end up with minus 6 is going to equal to 4a plus 2b. So we've got two equations. We've got this one here, which I might rewrite as by putting our minus on the other side. So let's rewrite that little guy up there. That's going to be 4a plus b equals minus 12. That's our first equation. Here's our second one. 4a plus 2b is equal to minus 6. And that's our second equation. It's a simultaneous equation, isn't it? So we can subtract those equations. We can do it by elimination. So I'm going to go equation 1 minus equation 2. Pop a minus in there. 4a minus 4a is nothing. b minus 2b is minus b. Minus 12 minus 6. So minus 12 plus 6, that's where the problem is going to be, is going to be minus 6. Divide by minus 1, b is equal to 6. That's our first answer. Now if we substitute that b back into either one of these equations, I might just pick that first one. 4a plus 6 equals minus 12. 4a equals minus 12 minus 6 is minus 18. A is going to be equal to minus 18 over 4. Okay, so there are solutions. We've found A and we've found B. I've just popped into Desmos to have a little look. Or A I've just cancelled down to from 18 over 4 minus 18 over 4 to minus 9 over 2. So the function would look like this. It would be x cubed, where the A was, I popped in minus 9 over 2, x squared, plus our B goes in, becomes 6x. So that's what our equation looks like. And it's saying it has a stationary point at 2, 2. So if I pop that into Desmos, there's the equation. This is what it looks like. It does have a stationary point at 2, 2. If I pop in there it is, at 2, 2 over here. It just happens to also have another stationary point, but we weren't asked to find the other stationary point. We were only asked to deal with the one that was 2, 2. Okay, that concludes our chapter. Our next one will be 3D. So that will allow you to go back and work through 3B in the textbook. So go back and have a look at the questions and get moving.